Hey, good morning, everyone.
Good morning.
Hey, good
Good
morning,
morning.
Kazuki. Good morning, Stephen.
Good morning.
Hey, good morning, Ian. How's everybody else? Andrea, Angel, Darlene.
Good morning, Professor.
Good morning, Andrea. Randy. So it looks like we have seven people, right? And I saw before I joined collaborate session, I just checked how many people were in today's forum, and there were nine. So yeah, nine people. So I hope two more people will join us shortly. Anyway, so we are now moving on to the new topic, uh, time value of money. And this is something, I mean, this shouldn't be, you should be familiar by now because this is not the first time. We started out with actually, the concept of compounding, if you remember, right? So, time value of money means, there's a there's a value that is value to money that is associated with time. Of course, we all understand. Um, basically, uh, if you have 10K today, right? Today's 10K uh, is much more valuable to you than 10K 10 years later, right? So at time zero, I better 10. That wasn't. Hence, it's called, time value of money. Now, think about it. Um, it's just like the saying, the a bird in the hand is better than two in the bush, right? There's an old saying like that. A bird in the hand is better than two in the bush. In other words, today's 10,000 is much better than $10,000 10 years from now. And it goes without saying. We all know. I don't know why I can't draw that well. Yeah. So the point is, you cannot give up today's $10,000 for tomorrow's 10,000, right? To make them equal, there must be a compensation. In other words, um, to give up today's $10,000, 10 years later, it should be something much bigger than $10,000. And that's the concept of basically, why we are putting money, why we require interest for $10,000 we put in the bank today. And also, that's why we are giving up today's consumption of $10,000 and invest it, right, for a much bigger return in the future. There's basically, I told you that investing is basically a trade off between today's consumption and future consumption. Isn't that right? You're giving up today's uh, consumption of $10,000, right, by investing it in a financial asset that will bring a much bigger return in the future. So, and the concept is very simple. Then, uh, this 10K is called present value or principal, right? this 10K today is called this 10K is called principal or present value. Okay. Then for this to be equal to something in the future, right? That should be called future value, right? So then the future value is principal times 1 plus the interest rate or return raised to time t, right? Or n. I mean, I'm going to make distinction between t and n, but here t is number of years, right? And this is nothing new because this is something we saw before because what was, when, where did we see that and when did we see that? At the beginning of the semester, right? In the house value example. And in the house value example, at the time, this R was all, it was G1, G2, G3, all the way to Gn. In other words, every year, the growth rate was uneven, right? Every year, the growth rates were uneven. It doesn't look nice, so. Okay. GT, right? So in our case, it goes to G10 because T is 10. So we did so basically what we did was to find the future value, right? In other words, the future value, the house value of I don't know, that's the touch point is not working there. In our case, house value 10 years later, right? Or which was the result of house value at time 0 times 1 plus G1 times 1 plus G2. I mean, that's what we did basically, right? And we keep going 1 plus G3 and keep going. We do this up to 1 plus G10, right? So everyone should be able to easily follow this because that's what we did at the beginning. And then if we will simply collapse to P0 times 1 plus G raised to 10, right? Because if G1 is equal to G2 equal to G3 all the way to equal to G10, right? Makes sense? That means if they are all equal, and that's called what? That's the geometric average, right? If they are all the same, that's the geometric average. And because it is geometric, it's average number, then it should be the same. The result should be the same. If we replace all this, right, by G, the average, right? And just to make sure, I'm gonna put the bar on top. With the bar, that means it's the mean, right? It should reach the same result, isn't that right? Think about it. If I it's a simple average example now, but I'm going to switch to simple average example. But if I find average height of everyone in this classroom, in this class, right? And we have n people. Let's say n people, n number of people, right? Which is 10 in our case. And how did I find average? I basically added up everyone's height and divided by 10, number of people, right? So that's, then if I find average, right? The sum of all the heights, let's say that's whatever, sum of all the heights, if average is, I'll write it. It's just like, I'll think about it. Sum of all the individual heights, right? 1 through 10. That H means height. And we divide it by 10, then that's the average height, right? But then if you multiply, then if we multiply average height by 10, we must come to the sum of all the heights. Make sense? It's the same idea, right? The products of all these, right? If we replace all these individual growth rates, right? Individual growth rates year by year, right? And by the average, right? And we can replace it with average because, average means, they are basically, if they're all the same, then that's average, right? If they're all the same, then that's average. So that brings a conclusion, right? And we know price of the house in year 10 is the price of the house at time 0, right? Times 1 plus g raised to 10th power. And that means we can generalize. Now we can generalize. Basically. Yeah. We can generalize. So future value, we'll call that future value at time n. Let's generalize it. Future value at time n is basically a principal or present value, right? Times 1 plus r. This time, we'll use the generalized notation of return, rate of return, right? Raised to nth power. Okay, that looks more like it. So this is called compounding. We already know So I'm not going to go over that again. It's called compounding. Compounding. Now then, it's not a new concept, but here's one thing. I'm going to have to introduce some new concepts. So now let's think about what this R is, because normally we use APR for that, right? All the rates are basically annual, right? All the rates are basically annual. But then it's actually APR divided by M. Our R is APR divided by M. Why? What does that mean? Now, compounding doesn't have to be annual. Compounding frequency doesn't have to be annual only. In other words, what that means is compounding doesn't have to happen just once a year. Okay? Compounding can happen any number of times, but periodically during a year, any number of times periodically during the year. So that means, so then what is M? So M is the compounding frequency per year. M is the compounding frequency per year. So M is it can be once a year or twice a year or 4 times a year, 4 times a year, right? Or 12 times a year. But just think about it. They coincide with natural cycle, time cycle, right? Once a year, annual compounding. Twice a year, semi-annual compounding, semi-annual, every 6 months, right? 4 times a year, quarterly, every quarter. 12 times a year, every month. Then you might think, oh, weekly? Yeah, it's possible. Theoretically, weekly, it's possible, but they don't use weekly compounding. If there is weekly compounding, then it will have to be 52, because there are 52 weeks in a year. And otherwise, $365, right? 365, daily compounding. And then you might wonder, is there higher compounding frequency than daily compounding? Yes, they can use theoretically, but it's theoretically. They don't. In reality, they don't use normally any more than daily compounding. But theoretically, hourly compounding, even minute by the minutes, right? Compounding by the hour, compounding by the minute, compounding by the second. It's all possible theoretically. And if it is, compounding by the hour, then you must simply need to multiply it by 24. 365 times 24. If it is compounding by the minute, then that times 60 to that, right? And so on. So then R is now more generalized. Okay, so this generalized R is called periodic rate. Periodic rate. It doesn't have to be APR anymore. It's periodic rate. Periodic rate. Okay. And then what about n? I mean, previously, remember earlier, I raised it to t, right? But then why n this time? Now think about it. It's it's automatic. When compounding frequency is, it can be not just one, more than one, like two, four, and during a year, right? Then during 1 year, I mean, if the compounding frequency is 4, think about it. If the compounding frequency is 4, there are 4 compoundings, right? There are 4 compoundings. Then, naturally, even if it is 1 year, there will be 4 compoundings. But if it is over 10 years, then there will be 40 compoundings. There will have to be 40 compoundings, right? So, therefore, n is now t times m. T is number of years. So n is the actual number of compounding, right? N is the actual number of compounding. So we need to make a little adjustment like that. We need to make a little adjustment like that, right? Actual number of compounding. So let's take a, let's do an example. Let's take a look at an example. Let's do an example. So I want you to download, okay. If you go into the topics folder, right, and time value of money, it may not be, is it visible still? I think it is still visible. And there are 2 files here, right? The second one is the Excel file, right? Please download that and open it in front of you. Okay. Yeah, all the videos are still visible, and this file, I want you to download it. And if you did, and I have already downloaded, so let me. All righty. Does it look like this? I mean, when you open it, make sure you have okay. I want you to, if the highlighted cells are already filled in, please delete them. If the highlighted cells are, okay, please delete them. So please delete all the highlighted cells. Do you have this file in front of you?
Yes.
Yes.
Okay, good. And then just check your data, input data. Is it the same input data? Do you have $10,000 for principal and 10% for APR?
No, we have 6% for APR.
Okay, all right, then fine. Let me change that to 6%. All right. And then 10 years. Is that right?
5 years. 5
5
years.
years? Okay. Well, let me change that to 5 years then. And the compounding frequency, M, is that 1 and 4?
Yes, it's 4 and 1. Yeah.
Okay. Oh, 4 and 1, not 1 and 4. I mean, what's on top? Is it 1 or 4?
4 on the top and 1 on the
Okay,
bottom.
make it, it doesn't matter. But, make it 1 and 4. Make it 1 and 4. Okay, make it 1 and 4. Now, so let's start. We know what to do. Oh, well, principal, so what's going to be the future value? Principal is 10,000, so P times, open parenthesis, 1 plus R raised to N. I mean, it's not N, it's T now, but, it doesn't really matter. That alone will already give you this. That should be your future value, right? Did you get that? Did you get that?
Yes.
Okay. Now then, what about, in this case, I didn't really bother with M because it's 1. 1 doesn't make any difference, right? Because if I divide APR by 1, it's still, the same thing. But if it is quarterly, then I will need to make adjustment, right? In other words, then, principal is 10K, open parenthesis, 1 plus. Now, APR, 6% APR will have to be adjusted by 4 because it's quarterly compounding. So every quarter when compounding happens, then it will be 1.5%, right? What applies every time, every quarter, it will be 1.5%, not 6%. So 1.5, 6 divided by 4. And then how many compoundings are we going to have over 5 years? And anybody can easily tell there will be 20 compoundings because it's quarterly every year, 5 years, 4 times 5, right? So we raise it to, and we need to open parentheses. We need to put it into the parentheses, T times M. Just, click it in, close parentheses. In other words, I did exactly this. Okay. Hit enter. Okay. Then we have this. So we have, what do you see here? Oh, it's the same 6%, same principal, same 10,000, same 5 years, but the more compounding, the more frequently compounded, or with higher compounding frequency, we arrive at a greater future value. Yes. Although this is the reason why there is a difference between APR and APY, right? I'm going to talk about APY later. APR is something we already know. It's the nominal interest rate, stated nominal interest rate. 6%, that's nominal interest rate, stated. And then, but compounding is just once a year. Then you arrive at this. And when compounding is just once a year, There's no difference between APR and APY. But what is APY? APY is annual percentage yield. Annual percentage yield. And what's the difference? It reflects the higher compounding effect. Same principle, same APR, same number of years, but higher compounding will result in higher future value, right? You might say, oh, it's just just about not even 100%, $100 difference. Look, you're going to see a big difference when we have a higher APR, higher T. Again, look, I did, I used, this simple formula, right? Without any adjustment, because M is 1, there's no need for that. But there's no harm. If I copy this, right, you know how to just, bring the cursor to the southeast corner and gently drag it. And then it's the same result, but the formula has been copied. And you can tell there's no difference. But, so why do we do that? Well, we have consistency. We have uniformity and consistency in the formula. And that's very important. We don't want to have different formulas every cell. We can have uniform and consistent formula, cell after cell, problem after problem. That way, we don't have to solve every problem every time. Okay? So the point is, now then, let's think about it. Let's change our APR to 10. Try changing that to 10. Change that to 10. Something's wrong with my keyboard. Why is it in French? No wonder. Suddenly it is. Yeah, let me fix that. Yeah. This is ridiculous. Switch input, press Windows key and space. Okay. All right. Something I pressed. Yes, I pressed something. Change that to 10%. Try changing that to. No, you shouldn't. If you put 10, it's going to give you 0.1. Give it 0.1, right? 0.1, right? 10%. And change this to 10 years. You see? You see, a bigger difference. The difference is almost $1,000 now, of course, because we have higher interest rate, right? And longer time. And I made, see, all of these things are linked. I made it, I linked it, making it equal to the initial data point. Then it's going to automatically, follow that because it's equal to B2, right? And also this one is equal to C2. So it's going to automatically right? So here, this time this time we are using two more columns, two extra columns, and these two extra columns are basically, R and N. But before we move on, did everyone get the same result? Did everyone
Yes,
get the
yep.
same? Okay, great. Now, since the input data already there, and you are just using my template, but at least these highlighted cells, we're gonna work on that. So let's find the periodic rate. So first, APR 10%. Periodic rate R is what? APR divided by N. So we do that. 2.5. Yeah, if it is quarterly, 10% quarterly, right? Divide 2.5. N is T times M. Okay. Then the future value will be simply P times 1 plus. The adjustment is already made, so we don't need to do this. We can simply use this. Principal times 1 plus R raised to N. Okay, that's exactly this one, isn't that right? Exactly this one. Now, for the rest of them, you might say, oh, okay, I'm gonna do this and do this. No, and do this, do this, do this. No, it's basically the same formula, same pattern. I mean, it's only different input data, but the formula is the same thing. It's these are the problems of the same structure, same pattern. So you don't need to solve them all over again. You'll just need to highlight these three cells, bring the cursor to the southeast corner, and just gently hold down the mouse button and drag it down. What do you see? And all these problems are instantaneously done. And then think about it. This is the beauty of Excel, right? If you were to do this by hand, you will have to solve the problem, each problem at a time, one problem at a time, right? But in this day and age, that's so time consuming and so inefficient. Inefficiency is stupidity, right? Inefficiency is stupidity because time is a very valuable resource, right? Why squander time just repeating the same work over and over again? And when I first demonstrated this, like 20 years ago, and in front of my colleagues and of colleagues from different departments, and the Josh Wolfson, who is the accounting department's chair now, was basically critiquing, was saying that, well, the students are so lazy, they don't want to do any math themselves, and if you are teaching them, isn't this just letting them teaching them to just copy and paste? But then my rebuttal is, this is not copying anybody's work. This is not copying somebody else's work. If you're copying somebody else's work, then that's plagiarism. But you are just replicating your own work. If you were able to do this, then just replicating your own work, what's the problem with it? Is that plagiarizing? You're plagiarizing yourself? I mean, is that plagiarism when you're copying your own work? Is it plagiarism? When you're reproducing your own work, is it plagiarism? So he was missing the point. I mean, when a student can do this on his own or on her own, that already proved that the student can solve the problem. And why then, if the student has made a point, proved the point, then why repeat meaninglessly, right? Why meaninglessly repeat the same thing over and over again by pencil and paper, right? Inefficiency is stupidity, simply. So, this way you can handle massive number of problems. Of course, you need to enter the initial input data. That goes without saying. But as far as the solution part is concerned, you can just replicate it, just in a few seconds, right? Now, so everyone got the same result? Let me know. Did you get the same result, everyone?
That's right, yes.
Okay, all righty. So let's see. How many people do we have? Any? Yeah, 9. Good. 9. That's the number of people here. Let's see. Try again. Yeah, 9. Good. Any questions so far? Any questions? Any questions? All right. So if there are no questions, then let me move on. So here, we know that the future value is like this. Then think about it. In our example, it was, it is very clear to have $26,850 to have how do I change this? Oh, yeah, let me. Okay. Oh, what did I just do? Now, it is very clear that okay, if you want this, right, in 10 years, right, with quarterly compounding, you must put in 10K today in the bank. So this principle is also called present value, right? Because it is literally the present value of this 26,850, right? 10 years from now, right? So then we can start. We can turn the turn this problem upside down, or we can question ourselves. Okay, if I want so if I want then if I want what was that, 26,850, right? If I want 26,850 10 years from now, if the interest rate is 10%, right? with quarterly compounding, with quarterly compounding, right? Right? And this already tells us that t is 10, right? What principal do I need to, what should be the principal? What principal do I need to put into the bank, right? Now we can have this type of question, isn't it right? If you have a specific target future value, you would want to know what should be the principal today, right? Now this type of problem is, exactly the reverse. Reverse question or reverse problem of future value, right? So we already know it's going to be 10K. We already know it's going to be 10K because we started from 10K and arrived at this. But think about it. Suppose we have a different target future value, right? Something like, okay, I want $500,000. 10 years now, 10 years from now, interest rate is 10%, compounding frequency is 4 quarterly. What should be my principal, right? We can ask this kind of, and then how do we answer that question? We can easily solve that problem because we know, we already know, because the formula is, we already know that the formula is P times 1 plus R raised to N is future value, right? And this is like, the only difference is previously, this was the unknown previously. Isn't that right? Previously, this was the unknown, but the rest of them are all known, right? But now this time, this is the unknown and everything else is known, right? And then question is, how do we solve for P? Well, this is, I say this to every class, every semester, and this is pretty much the indisputable law of, law of mathematics, that all equations, no matter how complex they may look, right, on the outside or superficially, no matter how complex they may look, all equations can be solved if they can be reduced to z equals x times y format. All equations can be solved if they can be reduced to z equals x times y format. Okay, this is the unknown. Think about it. That's basically, as long as you can identify the structure in any equation, you can solve it. And here, our unknown is x, right? This is our unknown. We want to solve for that. And then think about it. No matter what, x, solving this equation for x is z divided by y. Isn't that right? Z divided by y. Okay. And then look at the structure. Z, x, and the rest of that, this whole thing, this is y, right? And the logic is very simple. Logic is very simple, isn't it right? We all know 12, I'm going to have to rewrite this here. We all know 12 equals 4 times 3, or 3 times 4. And what is this? This is z. This is x. This is y. So you want to know, you want to find x, right? Which is, 4. It's 12 divided by 3, right? Can there be any argument about this? Can there be any dispute about this? No. Then that's basically what you do. And since, as I said, z is a future value, right? And our unknown is p, right? Right? Future value, right? So here, so this should be, and this should be P equals FV over 1 plus R raised to N. Okay, and in this case, this process is exactly the reverse process of compounding. The reverse process of compounding. The reverse process of compounding is called discounting. Discounting. So discounting, right? Discounting. And when you are solving for the principal, that principal is called present value because it's the present value of that future value, right? So everyone is clear about this. I mean, this is not that difficult, right? Not a difficult math just yet. So let's go to our example. So here we have, now we know what to do, right? I'm okay. All right. And we know the answer to this already. We know the answer to this, right? Don't we? We know the answer to this because they have to be $10,000 because this is just the reverse problem of the first example, right? Row 2 and 3. Although we know the answer, but let's find out. So since we already know, let's do this first. Everyone is there in row 15?
Yeah.
Yes. Okay, good. So all you need to do is future value divided by open parenthesis, open parenthesis, 1 plus, this is APR, this is M, So, and then raised to t times m times m, close parenthesis. Okay, hit enter. Yeah, 10,000. Of course, we know the answer already. I'll just drag it up, right? Drag it up. It should also be 10,000. But now, let's change the scenario a little. We can also do it like this, but I will leave it to you to explore that a longer. I call this longer version. It doesn't because we have 2 more columns. So side to side, the widthwise, it got longer, right? It got wider. the model got wider. But suppose this is, let's change this a little, future value, let's make it, $50,000. I cannot click it in, so then E14, let's type it in. Okay, that should be the principal, right? That should be the present value or principal. Present value. Or we can have a different APR. Make it 6%, which is more, and time, yeah, 5 years. Okay. Now remember, the higher the compounding frequency, right? The higher the compounding frequency, you end up in a bigger future value when we started with the same principle, but so the opposite is also true. When you arrive at the same future value, but different compounding frequency, the higher the compounding frequency, it takes less principal to arrive at the same future value, right? Or if it's the same principle, then smaller APR to arrive at the same future value, right? Does that make sense? Okay, everyone got the same results?
Yeah.
Oh, let me know. Did you get the same result? No?
Yes.
Why is everybody awfully quiet? You didn't get the same result? Huh?
Get it.
You did. Okay, only one person. How about other people? How about other people? You didn't get the same result? I'll take it as no. You didn't get the same result, huh? But please work it out. Please work on it. It's 1:02. It's about good time to take a break. We're gonna take a 10-minute break, right? We're gonna take a 10-minute break. Come back at like 1:12, 1:13. I'm gonna turn it into a formula view, right? Which doesn't really. And I'll leave it like that during the break. So please work it out. I mean, if you haven't got the same result, please look at maybe I'll make it a smaller. So yeah, well, all right. All right, let's take a break. So it's going to be 113, 114, 115, right? All right. All right, we're back. We're back. I hope you have caught up in the meantime during the break. If you didn't get it right, this is the time to get it right. And it was the time to get it right. So did everyone get it right?
Yeah.
You know, you just speak for yourself. You don't. I know you got it right before the break, but the other people, the rest of the class, did you get it right, everyone? If you're keeping just quiet, I don't know whether there was any problem or not, and if there's a problem, it better be corrected before we move on. And all right, so I will have to check individually. Stephen, did you get it right? Stephen, are you there? Andrea, did you get it right? Andrea?
Yes, I'm here. Yeah.
Okay, great. Angel, did you get it right? Angel? Angel? Are you there?
Yeah.
Did you
Yeah,
get it
man.
right?
Yep.
Did you get it right?
Yeah.
Okay, good. Darlene, did you get it right, Darlene? Darlene? Kazuki, did you get it right? Kazuki? Are you there, Kazuki? Leslyn? Leslyn, are you there, Leslyn? Randy, are you there, Randy?
Yeah, I'm here. I get it
Okay,
right, Professor.
you got it right. Good, good, very good. Okay, the other people were very, I guess, other people were just playing a hooky or something. Now, so let's move on. Our next question is, we all know when we have, we know that when we have an equation like this, right? When we have this equation, right? P times 1 plus r raised to n. There are 4 variables here, 4 variables, right? You understand what I'm? Now this can be 4 variables are, right? Each one of them can be the unknown, right? Isn't that right? Look, this can be the unknown, right? If future value is the unknown, then the others are known, right? We need the present principal is known, r is known, n is known, then we can solve for future value. But on the other hand, principal can be the unknown. Then the others are known, right? Well, we just did that, right? Future value is already known. We have a particular target future value, right? And we know what is the interest rate. We know how many years or how many months, you know. And then the only unknown is then what should be the principal, right? Makes sense. And then also R can be the unknown. That means, you know, the other things are known, right? The other things are known. Okay. And then next thing is N can be the unknown. How many years will it take? Right? How many years will it take? And then the others are known. right? The other variables are known. So each of these 4 variables can be the unknown, right? And 2 of them we have taken care of. Future value and present value, we have taken care of. And then if R is the unknown, we already know. We already know. You might, do we? When did we? Actually, we've done it. Remember, this is the, when we did house value example, we found this. I mean, suppose, just switch it with G. We found G, right? The formula for G was what? Future value over present value.
1 over t minus 1.
Yeah, 1. And 1 over n, because we are, time is more generalized, right? Okay, but at the time I just gave you the formula. Now this time I'm going to show you how this formula is derived. How do we get to this formula, right? Anything can be, any one of these 4 variables can be the unknown. Okay, so but I just want to make sure here what we did in the previous hour. We had all different sorts of M's, compounding frequencies. That's quarterly. This is semi-annual. This is monthly, semi-annual, daily, right? This is daily, right? So under all, scenarios, so now, why? So it's like this. First of all, suppose we don't know this, right? But let me. How did we get to that? Okay, let's erase that. So, all right. So if R is the unknown, right? Everything is known. So if we need to isolate R, but there is no way we can isolate. We cannot isolate R directly. So we need to isolate, basically, I've been telling you, everything is, as long as you can identify Z equals X times Y structure, right? That format, right? And we can solve for everything. We can solve for it. And here, our unknown is inside. Why am I? Our unknown is inside Y, right? Y is basically 1 plus R raised to N. So then we need to isolate Y first because we cannot isolate R directly. So if we isolate Y, then of course it's going to be Z over X, right? Which is basically, 1 plus R raised to N equals FV over P, right? and our unknown is R. So the thing is, we have two problems here. First, we have to, it's like this R is locked in a cell, and this is the N is the padlock, right? N is the lock. So to free this R from this cell, you must unlock this padlock. So how do we unlock it? How do we unlock it? How do we unlock? How do we unlock it? So now we need a little, review. We need a little review of, some algebra, right? First of all, we all know okay, and I showed some of that already in, actually presented it in here. Okay, properties of exponent. First of all, we all know anything raised to 0 is 1. Anything raised to 0 is 1. Okay, it's not 0, it's 1. I'm gonna, and you just memorized it. Probably in middle school and high school, you just memorized it. But I will show you the proof. There has to be the proof. In math, everything is proof. You must prove everything. And I will show you the proof. And the another is negative exponent property. Negative exponent is actually the reciprocal. Reciprocal. In other words, what does that mean? We all know what x squared is. Of course, that's x times x, right? But what is x to the negative 2? What's x to the negative 2? It's anyone?
1 over x squared.
1 over x squared. I already wrote it down. X to the negative 1, that's just 1 over x, right? That's just the way it is. I mean, that's how you write it. And then, product of powers, when if the base is the same, a to the bth power times a to the c power, cth power, a to the power of c will be just a raised to b plus c, as long as the base is not 0, right? And you just memorized it. But if you just use, try some. Now think about it. We all know 2 squared is 4, right? And times 2 to the third, which is 8. Let's try that. It's 4, right? Times 8, which is 32, which is what? 2 to the 5th. Isn't it right? And then 2 to the 5th is 2 squared plus 3. 2 to the 2 plus 3. That was what So if you just try out a few examples, then you can easily understand. Another thing, yeah, and if you understand this property, you can also understand this property too, right? Quotient of powers and powers of powers. And of course, when the base is different, right? A to the c, b to the c, but the exponents are the same, then you can just simply you can do 8 times b raised to c. Okay, and when the and if you understand this, you can understand this. But this is also what is what we want to know. That this will come in very handy. A to the b raised to c is a raised to b times c. So think about it. Just do a little experiment. So I'm doing 2 squared raised to the 3rd power. Then what is it? We all know this is 4. 4 raised to the 3rd power. 4 times 4 times 4 times. This is 64, which is exactly 2 to the 6th. And then if you think about it, it is 2 raised to 2 times 3. Come on. Isn't that right? So that rule, is simply, easily, demonstrated, right? But this is the property that we want to use. In other words, this property, right? Which is what? X to a raised to b is, x times, right? Now, you can also so that means another thing. I don't know if it was here. Yeah, here. Rational exponent. In other words, a raised to 1 over b. If you raise something to a fraction, that is, the radical, nth radical. If you raise to nth fraction of n, it's going to be nth radical. In other words, please say it, because I don't have time to look at the chat box. So here, we all know where did I do that? We know what x squared is. We also know what x to the negative 2 is. But then what is x raised to 1 over 2? Just x raised to 1 over 2. What is it? That's the square root of x. Square root of x. And just the same, x raised to 1 over 3 is the 3rd root or 3rd radical. Now you think, square root is, there's only square root. No, square root is something that, the root of the number that is root of the number that is squared of the root, right? But, there can be cubic root. In other words, 8, think about it. 2 is the cubic root. 2 is the cubic root of 8. 2 is the square root of 4, but 2 is the cubic root of 8. And 2 is the 4th root of 16. right? 2 is the 6th root of 64. So originally, you think, why is it there? Originally, for square root, we generally don't write it. We generally don't write it for square root, right? But for every radical or the root, we need to originally have to have that, right? So that way we can have even and we can extend it. Can have x to 1 over n, x raised to 1 over n is the nth radical of x, right? And also, if you have, then what is, then what is this? X raised to negative half. X raised to negative half. Well, then it is, we know x to half is, x squared. So then, and something to the negative power is the reciprocal. So then it is 1 over square root of x, right? Is everyone with me?
Yes.
Is everyone with me? Only one person. What about the other people? Do you follow?
Yes, Professor.
Yeah.
Okay, good, Randy. Okay, good. All righty. Someone wrote something in the, what's in the chat box? Leslyn, okay, you might need to reconnect. So here, this is the property we, as I said, this is the important property we need. This is the important property, right? Power of power. Why? Now let's get back to our question here. So how do we unlock? I mean, we can, transform. We can transform this equation, right, to this, because we need to solve for r, but it's inside this, it's enclosed. I mean, it's locked up in y. So we cannot directly isolate it, but initially we can isolate. We will have to isolate just y, which is 1 plus r raised to n. Then we need to open this. How do we open that? And for that, now let's think about it. Since we know, I mean, if we all know we can turn x squared to x by taking the square root of that. Isn't that right? In other words, by taking the square root, this is simply the same thing as doing this. Then it's x. Isn't that right?
Yeah.
Yeah. To make it more obvious, right? It's the second root, right? Or square root. So, and here, the reason the rationale is, the process is, think about it. Using that power of power rule, what we do here is x squared times x squared times 1 over 2. Then what happens? These two cancel out, right? So it becomes x to 1, because it's, right, it cancels out, it becomes 1, which is just x, right? And then, thanks to that, what we can do here is, so I'm going to go back there. We will then, what we can do, we can take nth root or nth radical of both sides. So in other words, the left-hand side, I'll just put it like this. Left-hand side, it's not a big deal. So I'm going to do 1 plus r raised to n raised to 1 over n. And if you, and in an equation, whatever you do to one side, you must also do the same to the other side. That's the only way the equality, right, that, that equality relation will hold, right? You understand? No matter whatever you do, no matter what you do to one side of the equation, you have to do the same to the other side. Then you will, right? Then this will be raised to 1 over n. And then think about it. This side will be 1 plus r raised to n times 1 over n, right? And what? They cancel out, right? And in the right-hand side, it will be, I'm not going to write this anymore. I'll just, okay, the thing in the bracket raised to 1 over n. Now the left-hand side, r is, without any exponent, this is 1 plus r. So it's free. Now, 1 plus r is free. It's 1 plus is 1 plus r, and the right-hand side, the thing in the bracket, right, raised to 1 over n. Now then, finally, think about it. We need to isolate r only, r. Then what do? You move this, you move 1 to the other side. Or, in other words, you subtract 1 from both sides, right? So we will have only r on the left-hand side, and then the right-hand side is going to be f(v) over p raised to 1 over n minus 1. Okay? Hence that formula, right? That's how we got that formula. When we were on house value example, because, it takes this much time, you were not yet prepared for this. So I just threw this end result. But, this is how, right? This is how we arrive at this formula, how it is derived, right? So we now know. Okay, we now know. So any questions? Any questions?
No.
Okay, all right. How about the other people? Are you guys all, are you there? Are you guys dead or deaf or? There's something having trouble hearing. Yeah, I'm afraid. you will need to adjust your computer setting. I guess that's the only way. So let's go to our next example. Here we have this. Oh yeah. Row 18. Now this is basically finding APR, right? Well, your principal is 10K, future value 30K, right? And then compounding frequency is just once a year, but here compounding frequency is 4 times a year. So and the row 19. So we're going to do 18 and 20 because 19 and 21 it's about n, and that's going to be another thing. So here let's find. So basically, this is easy because this all you need to do is, okay, I'm gonna do, okay, F your PV is to 1 over T is n in this case because T is n because compounding frequency is just 1. There's no difference. And I would like to click it in, but since this formula is hovering or covering that cell, I cannot click it in, so I will manually type it in. Since C18 is C18, right? Close parenthesis, -1. And there you go. It should take 24.57% interest, such a high. So this is not necessarily an interest rate. I mean, if you have $10,000 put into some stock or some index fund, and if the index fund, that stock grows on average, like 24.57% a year, in 5 years you'll reach $30,000, right? You can triple your money in 5 years. Next, here, compounding frequency is 4. Then what do? You'll just need to make adjustment. Either that, or you can add 2 more columns and find R and N, and do it. Next example is that. So here, I'm gonna have to. It's the same still. F3 over P is 2, 1 over. Now, it's not 5 now, it's 5 times 4. So it's going to be C20 times D20, C20 times D20, parenthesis, -1. Oh, no, something's not right. Over, yeah, here. Okay. There you go. Then that means quarterly, it will, this is quarterly rate actually, it's quarterly, but the question is, what's the annual rate? Then the whole thing, this result will be multiplied by, again, M is in D20. Okay, multiplied. So then annually it will be 22.57. And you remember, the greater the compounding frequency, the greater the future value. But if the future value is the same, that means it would need just a smaller return to arrive at the same future value. Okay, makes sense. So this may seem a little complicated. Then we can also do this. Add two more columns like this. Okay, we'll first find R, periodic rate, which is, it's called, FV over T raised to over N, raised to 1 over N. N is in F25. It's not filled in yet, so it's going to give you, as of now, or just now, it's not going to give you anything. But when we have, so then, what's N? 20. 25 times 5 times 4, 20. And we get exactly 565, which is, quarterly rate. But then if we turn it into annual rate, APR, then simply this times 4. Right? So we get exactly the same number. Okay? Everyone is good with, okay? Everyone is good with this? Are you with me?
Yes, but our Excel is different than yours, so we maybe have time to adjust the original number.
Okay, what is different? I mean, you mean input data? Input data is different? What is different?
Yes, because in the row 25, the
Mhm.
cell of G25 is 220,400, so it's kind
Oh,
of different.
okay, so then make it 30,000. You just make it equal to this, right?
Okay.
Then, as long as the formula is correct, then everything will be the same. Okay. All righty. So I think this is a good time to take another break. So it's 1:52. So we'll take a 10-minute, and I'm gonna turn it into a formula view so that you can catch up during the break. Okay. Turning it into not just the whole thing. Okay. All right, we're back. We're back. So our last pitch. I mean, I would like to remind you also that the midterm has been already announced, right? It's not visible to you just yet, midterm instruction, but it's going to be available from tomorrow, Saturday. It's going to be due on Monday. Now, this is and so it's not visible to you just yet, but it's there. Okay. My only concern is, okay, where is? Okay, that's my only concern is that it covers, basically financial statements and time value of money. And we can't quite finish time value of money today because we can we cannot even finish every time value of money falls into two groups, right? Two groups of models. It's getting too big, I guess. So, and if you have been following, following the main lecture, you would know it breaks down into a single cash flow model and multiple cash flow model. We cannot quite do multiple cash flow model. It takes, it requires at least 2 more days. And even single cash flow model, we cannot quite finish this because in single cash flow model, we have to address all four variables, right? And we have done, and future value is the unknown, present value is the unknown, rate is the unknown. Yeah, we've covered this, right? But what about n? When is the unknown? We can touch on that, but it's gonna take a lot of time to finish it. And today, most we can delve into that, but I don't think we can finish. I mean, given only about 20 minutes, but but the exam is based on the main lecture. I mean, I've been telling you over and over. Collaborate session is only a review. So I'm sure if you have studied main lecture carefully, then I'm sure you can do that. Now, so we are moving on to the next question, which is, so when n is the unknown, how do we solve for that? Again, we know the base formula is this, right? And here, we are in a dilemma. Why? Think about it. I've been telling you, as long as you can identify z equals x times y structure, right? we can solve for anything. But this is not z equals x times y structure. This is rather more like, this is not like this, but it's more like z equals x to the x raised to y structure. Okay, it's x raised to y structure. And then if that's the case, so y is the exponent here, right? Y is the exponent here. So then how do we solve, when y is the exponent, how do we solve for that?
Log on both sides.
Yeah, we take the log on both sides, you know. Yeah, that, so then y. So we need to understand the nature of logarithm, right? So here, first, we can transform this equation. We can transform this equation as much as we can. We should first transform this equation to the best of our ability. Then it becomes, of course, FV over P, right? Then on the right-hand side, it's going to be 1 plus R to the N. Now it is exactly then, you know, it is exactly this structure, right? Now then, this pattern is exactly this pattern, right? And then, you know, what is log? Logarithm is basically a way of expressing a large number by the exponent of its base. So we all know, I mean, it's not a difficult thing. To start with, for example, we all know, why red? 100 is 10 squared, right? And 1,000, we all know, 1,000 is 10 cubed. And so on. I mean, you know, then $1 million, right, is 10 to the 6th. 1 billion is 10 to the 9th, right? And so on. 1 trillion is 10 to the 12th. Oh. And then, you know, again, you know, 1 billion, 9 zeros, right? Billion has 9 zeros, so 10 to the 9th. And trillion has 12 zeros, so 1 trillion I'm not gonna write put zeros anymore. 10 to the 12th. I mean, we can do this, endlessly, but then how does this help us? I mean, can we not just write 1 trillion, instead of 10 to the 12th? Not only doing it this way saves time and space, right? Time and effort, right? I already know by putting 12 zeros, that takes a lot of time, takes more effort. So why don't we just spell it 1 trillion? Okay, but then you have to understand when you write the word is not a numerical data. You have to understand you can't use text. It's a text, and on Excel or any quantitative uh, modeling program, any we need quantitative data. Text is not data. Text is text. It cannot be processed. I mean, you put 1 trillion. How does Excel recognize 1 trillion? I mean, it will just recognize it as text, not as numerical data. So it cannot be processed. So if we have to put a lot of zeros, it's easier to do it this way. And then here's the thing. How does it help us? For example, a large number is really cumbersome, but it's sometimes, is inevitable. Why? Suppose we are trying to show the distance between the Earth and the nearest galaxy. And the nearest galaxy to our galaxy is Andromeda galaxy, right? If I'm not mistaken. So we are here. This is Earth, God's green Earth, right? Blue Earth. Okay, they say God's green Earth, so let me make it green. On God's green Earth. And what do you think is the distance between, let's say this is Andromeda. Andromeda galaxy. How do you express the distance between Earth and Andromeda galaxy? I mean, just putting it like this, does it make, give you any sense of how far it is? It would be like, hundreds of light years away. And one light year is like what? That's the distance the light travels, a year. And it's like 8 billion something miles. Even between the Earth and the Sun, of course, for sun's light to reach Earth, I think it is like 3 minutes. So it's not even a light year. But the idea is, if this is the distance between Earth and the Sun, and let's say this is like 10 billion miles, 10 billion miles, and then that's not even one light year, right? But like tens of light years away, or hundreds of light, then this cannot even. I mean, the scale should be, between the distance between Earth and the Sun should be much smaller. But let's say that's 10 billion. Then the distance between, just hypothetically, distance between the Earth and the Andromeda galaxy is 10 billion, 10 times this, or 100 times this, or 100 times would be times 100, but this is like whatever, that so 10, not 100, but it's just 10 times already, 10th power, 10 billion. Oh, that would be a lot. So let me just be less, maybe squared, 10 billion squared, billion, 9 zeros squared, right? 18 zeros. I mean, 9 zeros. Oh, no. What am I thinking? Yeah. Squared is 10 billion times 10 billion. So that's 10 zeros times 10 zeros, right? 10 zeros times 10 zeros. 100 zeros. 10 zeros times 100 zeros. How they, right? That's 100 billion miles. That would be 100 billion miles. How would you express 100 billion miles on a finite space? There is no way you can do that. Huh? So, there's no way you can put, like 100. It would be, 100 times this. I mean, even so. Easiest way to do that is by using a logarithmic scale. Because if you use logarithmic scale, right, each one of these, right, on a normal scale, this would be 2, this would be 0, 1, 1, 2, 3, 4, 5, 6, and so on, right? 2 is 2 times, if it is 2, it's just 2 times this distance. If it is 3, 3 times this distance. But on a logarithmic scale, this is 10 times. This is 100 times, right? 1,000 times. In other words, 1,000 times, and so on. In other words, on a logarithmic scale, each notch, whatever you call this, notch, right? Each notch is not just double of the previous, but it's powers, right? So if we do that, if we can use logarithmic scale, so think about it. Actually, this point is 10 to the 6th million times, not 6 times, right? This is then 6, 7, 8, 9. This then this point is 10 to the 9th. In other words, billion times, right? Right? 10, 11, 9, 10, 11, 12 trillion times 10 to the 12th. So we can condense a huge number. We can condense a huge number into more manageable, manageable amount. But of course, your mind should be more imaginative. In other words, you should be able to understand that this is, trillion times, not 12 times, right? But this way, we can manage a huge, a number more easily, right? That's why we need to use logarithm. Why? And logarithm, in this case, this is called base, right? So in other words, 100 is squared term of the base. So if we turn it into log, it's going to be base 10 log of 100 and base 10 log of 100, which is, base 10 log of 10 squared. Now, we know there is a reason why I use the 10 as the base, because all these numbers are powers of 10. So we can easily reduce it, simplify it to 2. So when just to the exponent. So think about it. When the base and this is also the base, so basically they cancel out, right? And this becomes, but before we do that, when we have an exponent here, we can move it. We can bring it down to, this becomes, we can bring it down like this, like as if it is a parameter or a coefficient. So this becomes 2 log base 10 log of 10. Think about it. Base 10 log of 10 is just 1. It's just itself, right? Base 10 log of 10 is just itself. So, so that's why, it just cancels out 1. So then what? That's 2. In other words, that's why that 2 represents here on the time on this distance line. 2 is 100 times, right? And so on. In other words, for 10 to the third, right? You take log of 1,000, base 10 log 1,000, and then it becomes, we all know, 10 to the third. So it becomes 3. And it is this, and also for anything, for billion, right? Log of 10 to the 9th. And this property, you can bring this exponent to the front and base 10 log of 10. This property is very crucial to our problem. It's a very useful property, right? It's a very useful property. So we're going to use this property to solve our problem. And then the next thing is, this is called common log. I mean, log, think about it. Oh, so all the logs have only base 10? No. You can use 10 as the base. I mean, then in that case, it's called common log. And typically, there are three types of logs that are most frequently used: common log and binary. Common log, and binary. Binary log and natural log. Okay, so and we are going to use natural log because so two things here: this property of log, and natural log. And the reason we can, it's not that we cannot, but it's not easy to take log of odd and odd numbers, not just odd numbers. What should I say? Think about it. It's easy to take common log of the numbers that are powers of 10, but then other numbers. Can you take common log of numbers like 13.23? Yes, you can, but it's not easy to easily visualize it, mentally visualize it. And besides, we'll be dealing with numbers that can be even irrational. Rational means, rational number means, even if it in fraction, even if it is a fraction, it goes to a fraction. It stops at some point. It stops somewhere, or repeats. But irrational number means it doesn't stop. It keeps it keeps going on with different decimal parts. So for such a number, we cannot use a common log or binary log. So we'll have to use natural log. To understand natural log, then we have to understand Euler's number. So this thing, we'll have to talk about it in after this weekend, which includes Monday, right? Martin Luther King Day. So, all righty, that's all the time we have for today. Any questions so far? Any questions? Any questions?
Oh, Professor, you said we don't have class on Monday?
No, we don't.
Okay.
Yeah, it's
And also,
King Day,
yeah, about the midterm, when is the due date?
Monday is due date.
Okay,
Monday, yeah, midnight, 11:59 p.m. Monday.
got it.
You don't
Thank you,
have,
Professor.
yeah. You can go directly to the announcement and check, right? And don't rely. I say always, this is a common sense in everything, in any official business. Nothing is done by words. Okay, there's no word of the mouth. Yeah, it goes by, it goes by writing. Everything has to be in writing. So you go to the writing. This is the, there's an instruction there. Writing. Everything must be in writing, right? So that there will be no later, oh, was that what I said? No, there should be no chaos later. So I posted it there. You should, just take advantage of that. Okay. All righty. So that's it for today. Have a great afternoon, and have a good weekend. Don't forget to do your midterm over the weekend. Okay. All right. So I will see you guys next Monday. I'll stop sharing. Are you there? Huh? Just other than two
Yeah.
people, Randy, I know you are there. Yeah, I know. All right, darling. So have a great
True.
afternoon, Kasuki. I will see you guys Monday. I'll stop sharing, stop
Tuesday.
recording.